Okay, how does that look? That looks pretty good. Well, the last two talks were a great setup. My name's Mike Miller. I'll be talking about Apache CouchDB. So since I'm a new face associated with the project, let me give you a bit of an introduction. Like I said, Mike Miller. I'm a founding member of Cloudant, which was a startup founded by three physicists, particle physicists at MIT, and is now grown and about to go into open beta at the end of this week. My background is in big physics, and I'm actually still a professor of particle physics at University of Washington. I ended up going there before we actually founded the company. And it's kind of interesting that I'm up here talking about CouchDB because, you know, I worked on a project at CERN at the LHC where the spontaneous data rate was of order 100 petabytes per second, which is something that you clearly can't deal with in pure software, clearly can't record. CouchDB is something that kind of started with the notion of big data. But if you listen to the conversations these days, I think there's a bit of a feeling that it's focused on other things initially. So what I'm here to talk about primarily is what is CouchDB, who uses it, what is the roadmap, and what kind of problems has it solved for the people that have put it into production. So off the bat, CouchDB is a schema-free document database. The database is a web server itself, so it's already going down the path that Cliff talked about in the last talk. It's really focused initially on being robust, dealing with high concurrency systems, and being fault tolerant. I'm going to stress that over and over as we go through. It's a RESTful API, speaking JSON or HTTP. It has a nice web admin console. It's client-side JavaScript. But one of the things that separates it from a few of the other projects is, I didn't actually put it here, is one of the projects that didn't come out of a specific company to solve a specific need. It was largely motivated by the vision of one person, Damien Katz, the founder, who's now at IBM. And I think his love of documents and document stores in general probably sprang from the Lotus project more than anything else. But it has evolved in a fairly unique way. One of the things is it has MapReduce for generating custom views. I'll tell you a little bit about that and what problems it solves. One of the key differentiators also is it's focused initially, and this is something that Cloudant's really thrown its resources behind, on bidirectional replication over the wide area network between two CouchDB servers. And really, this was very well set up by Cliff in the last talk, but one of the very recent focuses over the last year has been this idea of the Couch app, serving lightweight HTML and JavaScript apps directly from the database server, taking advantage of this MapReduce view framework, and some recent additions to it called show and list that allow you to reformat the JSON, iterate over it, and interact with it in a way. So that vision is to some extent already becoming a reality for a lot of applications that you'll see on the web now. Okay. So I sent out a lot of requests for feedback from the Couch community about people that use it and people that have chosen not to use it. And I've tried to paraphrase that here in the truest sense that I could from the feedback I got. But for those people that did choose CouchDB, they tend to be very happy. And the reasons they chose it were that, number one, it's simple, it's robust in production, it deals gracefully with high concurrent loads, and overall it was a fun project to set up. And I'll walk you through 5 case studies of where it's been successful in production. For those that didn't choose Couch, and these are some of my best friends from the physics world, from the business world, I try to really paraphrase this new. It has to do with the fact that there are features that they wanted, ad hoc queries, authorization, auto-sharding, clustering, et cetera, a general feeling that it was maybe too slow, and that it was too new, and it was still in alpha. Well, I'm not going to walk you through the list of all the things that are new, but there's been a lot of acceleration in this project. It's now an official beta, and there's quite a few companies that have gone from interest to adoption on the project, and I'll try to walk you through the reasons why they do that. I think BBC was one of the first big companies to go there. Most recently, Scoopler and Collecta are 2 out of the 3 top real-time search engines, which are now powered by CouchDB through Cloudant. And then there's a host of new companies that I think are new products that are rather visionary. Anybody that uses Chef to configure their cloud knows that Opscode uses CouchDB underneath. 2 weeks ago, the Ubuntu Linux project formally incorporated CouchDB. That goes out in the 9.10 release to over 13 million users. And then I think it was last week, Mozilla Raindrop opened up, which uses Couch. So there's a lot of users. There's 3 books being written. There's a vibrant community. And as a founder of Cloudant, CouchDB plays a large role in our vision for the cloud. And so we, along with a few other companies, are actively commercially developing on the project and contributing back into the open source. So I would say it's a rapidly maturing project. A lot of things have happened recently, well before these companies actually chose to adopt Couch. So I just want to step back a second and ask the question, what is it that really drew them to Couch? And I think it's the idea of a bit of vision and a bit of a potential paradigm change. This is a great quote from 2 years ago, actually, from one of the founders of Django. It says that Django may be built for the web, but Couch is built of the web. He goes on to say that he's never seen software that so completely embraces the philosophies behind HTTP. And ambitiously, this is what the software of the future looks like. So this is a great quote. It definitely makes you feel great about the project that you're working on. But then you can ask the question about, from a business standpoint, is this the type of thing that should really get you excited? And I think the answer is yes. Here's a great quote we got from Bill Warner in a Y Combinator dinner, where he was talking about building Wildfire, really well-funded project that didn't succeed. And one of the reasons is the internet happened and we ignored it. In retrospect, that was a mistake. And I think that the example here is that there are new technologies that definitely do enable new business. And I think there are certain parts of CouchDB that really take you in that direction. So I'm going to step back and take a brief look under the hood, just for those of you who aren't really familiar with it, what the interface is and how you interact with it. And then I'll finish up with 4 or 5 case studies. So to first order, CouchDB is a document database. You construct JSON documents and trade them over HTTP with this REST interface. Documents are pretty simple. They're reserved fields. Documents have an ID, so it's a key value store, very much like Dynamo. Documents have a revision number, which is the way that CouchDB does multi-version concurrency control. So it's deterministically generated, and every process, every interaction with the database or transaction is actually interacting with an MVCC snapshot. And what you don't see here is that documents can have binary attachments, so you can stream blobs to disk that are stored in a slightly different manner. So you have great flexibility here in a completely schema-free system. It's absolutely up to the application developer how much structure they want to impose on the data. Okay? And there are methods within Couch now in the last release that allow you to put validation functions into the database so that you can actually maintain structure there at the server level, and to do a lot of server-side manipulations that used to have to be done in a get, change, push request. But the fundamental thing about Couch is that it's very robust. It's a tail-append, never overwrite model. And you can literally stop this thing with a Control-C termination. And so in the event of a power failure, you just restart it. There's no repair. There's no log replay. This has a lot of advantages, one of which is that you can take snapshots, okay, with very simple commands. And the price you pay here is that by default, you're interacting with the disk. And we saw the lesson 2 talks ago in the Voldemort that if you choose to flush everything to disk, yeah, you're going to stay around the millisecond per transaction scale. Okay? But that is a configurable level of durability, and you can choose the rate with which you f-sync if you want to gain better throughput. But out of the box, you can be guaranteed that a write accepted by Couch is flushed to disk. And that's one of the things I think that generally was why this has been chosen for some production systems that we'll see. The other big pillar in Couch design was concurrency. And it was built from the ground up not to be lightning fast for individual transactions, but to make sure that in the Erlang fashion, it's going to deal gracefully with high levels of concurrency. Okay? And that's a theme you heard from Dynamo. We'll hear it from Riak later on. But the Erlang approach here is really modeled well in the database design that each transaction is a lightweight process, okay, in Erlang. So 1 process per connection. And each of those transactions works with an MVCC snapshot of the database. So it's an eventually consistent model, as we'll see in some detail later, that's implemented in Erlang. And the big point here is that the performance gracefully degrades under heavy concurrent load. So the numbers out of the box aren't startling. It's that of order 1,000 operations per second per machine for a standard machine. But you know that you're going to hang somewhere near that, okay, in production. So what you see is what you get. The REST API is very straightforward. We saw what a document looks like. That's simply sent over HTTP to the general put, get, update, and delete interface. Okay? So single document key value operations are very straightforward. And this is just a screenshot of the web browser called Futon. This is a client-side JavaScript app that's served directly out of Couch. And the interesting thing here is that the test suite actually lives in this client-side JavaScript. So that philosophy is really embraced already. But one of the things that is so powerful about Couch is the way they do views. Okay, so key value stores are great, but you often want to query, manipulate, reformat your data, and in particular, do detailed analyses in real time. And Couch does that by using MapReduce views. So a view is a persistent representation of the document data, and it's really, at this point, pretty close to the metal. You're writing the real map and reduce functions yourself. You write those in a language of your choice, primarily JavaScript, and you upload those to CouchDB. Okay? So it's a very simple way to interact with the data and something that at least JavaScript, Python, Perl developers are fairly comfortable with. Each view has a map function, may also have a reduce function. And it's a standard MapReduce style, but what Couch has is a pretty rich view collation, the way the keys are sorted, and I'll show you that in a minute. And it has a very rich query API built on top of that. Okay. What this looks like is here's a simple JavaScript MapReduce view that you would upload or just type into the Futon interface that gets run on your data. And you can see that it's fairly straightforward. The map function emits a key and a value. The reduce function operates on those key values to manipulate the data further. This is simply a way to add up all of the titles by a given author, if you wanted to. You can do fairly complex things in a very small amount of code. I'm not going to go into the details of what this reduce function is, but this is pretty much the standard thing that you'll see over and over here, and is a model that can just be copied to a large extent. But in this top one, what you're doing is doing a word count in a bunch of text that's stored in a document property called blob. You simply split it, you omit it, you lowercase it, and then you emit a value or a key. Key is the word. You can even tell what document it comes from, and then you emit a value of 1, which allows you to count the occurrences of those for that word in that title. The really interesting thing about Couch is it does MapReduce views incrementally. Okay, so the results are stored in a B tree. So every time you want to do a query, you don't have to blow through the data again. And in the case where you've already built a view on your data, and you're modifying some of the documents that are already in the database, it knows which parts of the view need to be updated when you change that database. So it's a big difference right now from kind of the data warehousing, blow through the data, Hadoop style, or Dryad style, to something that's truly incremental. The way it does it is by computing the view and saving the results in a B tree. And in a MapReduce case, what happens is the map results get stored over here in the leaf nodes, and the reduce results are built and can be queried at various levels of reduction as you go up the tree. What this means is you have a tremendous amount of flexibility. You can emit something in your MapReduce that has a very granular key, okay, a lot of dimensions. Classic use case is in time, where you go all the way from year to seconds. And then in your query to the view API, you can hit the already cached results as you integrate across that granularity, okay? So you get a lot of power out of a small amount of code. And I'll be glad to show you some examples of that outside if you're interested. Because it's kind of non-trivial, and it's one of the things that we haven't done a great job in the Couch community of really broadcasting and teaching to a large extent how to take advantage of that. But the other real killer feature behind Couch is bidirectional replication. So this is peer-based bidirectional replication between 2 or multiple Couch servers. And it's mediated by a process which runs on both. And you can do either push replication from one to the other. You can do pull replication from the target from the source. And you can set this up to be persistent. And you can set it up to be fault tolerant. The idea is that you replicate a subset of the documents meeting some criteria, which can be defined in the next release by a custom filter. This is pretty cool because it means that you can choose to pull down, say, to your laptop from your production cluster, some filtered set of data on a daily basis, interact with it, and maybe push it back up, okay, to your system. I'll show you how this works in use. The other great thing is that, applications in Couch speak, they're called design documents, which have your map and reduce views, along with these Couch apps, which are the HTML and JavaScript served out of the database server. They get replicated too, okay? And you can do a lot of really amazing things with this. The ideal use case is ground computing. You have a machine that's on and offline. you have some updates to that state, and then you want to broadcast the state back into the cluster. And I think that's what we'll see with the Ubuntu One project. So the way this basically works out is you have a source and a target. Say this is push-based replication. And the Erlang processes are talking to each other and saying, what updates do you have since the last checkpoint? Okay, since X. There's a response. Says which of these are you missing? It's decided which ones need to be pushed, and then you implement a bulk transaction to push those documents over HTTP. So this part of the system is working over HTTP, not using distributed Erlang. And that goes to one of the questions before, which is suppose you're talking about something that's going over the wide area network. Distributed Erlang over the wide area network is a tricky business and something that we haven't had a lot of success with. And so this is a very nice way to decouple intra-data center from inter-data center issues. There's challenges that come with this. And the final thing is the checkpoint. The challenges have to do with conflict resolution. I have a whole bunch of backup slides that I can go through if you're interested, but I think it's probably a little too detailed for this crowd. But replication can introduce conflicts in a multi-master setup. Okay? So suppose you have a document with the same key written to one database, a document with the same key written to another database, then you replicate them together. That conflict has to be dealt with, just in the same way you have writes happening at the same time in an eventually consistent system in the same database. Okay, so what Couch does is it deterministically chooses a winner, right now based on update sequence, or in the cloud model based on vector clock. And it chooses a winner, but the loser isn't thrown out. Okay, the loser is saved, and if the application wants to come along and resolve that conflict in a custom manner, it can be done. Okay, and so with each document then that has had a conflict, it's stored in a history. And that history, even the conflicting documents, are replicated through the system as well. So it's never too late to go back and resolve that conflict in a new fashion to the best of your ability. So that's one very powerful thing here. This was a hard thing to get working smoothly. And my co-founder, Adam Kokolowski, has thrown himself behind this full system. And I have to say, it was a little humbling coming from our distributed systems and storage-based background to realize all of the challenges in the system and keeping it running smoothly in production. But it's very solid. It's been running in production for quite some time, and all of those changes have been pushed back into the open source with the last release. This allows you to do a lot of very cool things with the architecture between two or multiple servers. Okay, so we're still talking servers and not clusters, but you can have the typical master to end slave relationship. You can have multi-master setup, which allows quite a few scaling possibilities. And then I think the greatest thing for ground computing is you can deal with many-to-many replication, okay? And you can deal with a case where some of those replica peers are coming and going on and off the network. That's challenging but very powerful, and it enables a whole suite of new applications that can be written based on this. Okay, so I went through that pretty quick in 15 minutes, just about right. And I want to walk through a few case studies here. And then I want to open it up to questions. So by the way, you should stop me at any point if you have questions along the way. So I'm going to look kind of in semi-historical order about companies that have chosen to build their applications on Couch. I'm not going to show you the whole application stack, how it shakes out. But I'll just try to, with a few bullet points and one example, show you why they chose it. So one of the first adopters at scale was the BBC. I believe the entire BBC online website now is powered with CouchDB as the storage engine. So they had a unique case that they definitely needed flexibility in the schema because their data sources are always changing. They needed something that was robust, and their choice was largely driven by benchmarking different options and choosing the one that was graceful under high concurrent loads, dealt with that in a graceful fashion. This was actually being plugged into a custom application stack that they had. Their architecture already had a way to distribute data across the different storage engines. Okay? So that's not something that was a design feature that they needed at that time. And so they're choosing Couch just as a basic key value store with some basic MapReduce queries on top of that to get data back by different types of keys. And CouchDB was actually chosen from a pool of competitors, and I wish I could have gotten the graph that showed you, but it was very much like the lesson that you saw in the GILT talk. And they have a couple plots, and one of them shows the response time as a function of concurrent connections to the database. And there's this huge sharp peak, which was memcached DB, which was just blazingly fast. until the size of the database got too large or the number of concurrent connections went up, and then it had this long and awful tail. And they show a couch plot that just shows that, the performance was averaging around 500 to 1,000 operations per second, and it went rather smoothly. This was showed at the Erlang factory. And that was taken from their actual production system when they tried different backends in place. And so this has proven to be robust to them, and I think the key things there are the fact that it needs to be robust to single server failure. You need to have a robust way to back up data and to have quick mirrors built. And so there, this tail append copy on write model of Couch and the ability to replicate between servers was a key characteristic that drove their decision. Sorry, was there a question? Okay, the next case is Meebo. So I got some great quotes back from one of the Meebo developers, VJ, on the Couch list. And I'm just going to just tone this down a little bit and then condense it. When I asked them, why CouchDB, they said that, they were looking for something that was flexible, it was fast, and it had to be queryable so that it can scale to hundreds of millions of documents. Okay. They had to have a seamless failover mechanism. And CouchDB has really suited those needs, and in fact, it's gotten so popular that they're working on migrating a lot of their sharded MySQL stuff into Couch, as well as writing their internal dashboards as Couch apps. Okay, that's a pretty unique thing, and that goes at lowering the barrier for people to get up applications that have scalable backends, I think. The things that really that they love about it are the schemaless design, because their data sources are changing over time. They need to be able to interact with that. The flexibility of building custom views to get exactly the type of query that they want. Replication has been a killer. And in their case, they have a large base of JavaScript developers, I think, that really love the fact that they can write queries in a language that they are really familiar with. One of the things that Meebo did is they built their own custom sharding layer on top of Couch that they call Lounge, which is a custom Nginx twisted sharding layer. And one of the things that they would really love is to see that incorporated back into Couch. And that's what we're working on at Cloud, and especially with Cliff's help, is to take that Dynamo and what I want to say, architecture that's become rather classic and standard now, and push that back into the Couch trunk so that you don't have to worry about sharding, so that auto sharding takes place. Of course, their wishes were speed and stability, and I think stability here was specifically referring to replication. And with the last release, this has become really a fairly rock-solid part of it. And speed and optimization is something that I'll return to at the end. But optimization has not been a big part of the Couch project to date, and that's starting to change. So the overall takeaway message here was that for Meebo, this was really a success. Let me talk about something that stresses the real-time aspects a little more. So Scoopler is one of our Y Combinator peers from summer of '08 in Boston, and real-time search engine, and actually Cloudin's first customer. So they're a real-time aggregator, and we're seeing a lot of these popping up. And so they're an aggregation service for large and growing disparate unstructured data sets. So they're catching the Twitter feed, they're catching friend feed, they're catching pictures, they're catching videos. They're storing it all and indexing them themselves, and then they're running custom analysis on that to do ranking and sorting, and then they're actually presenting that back out of the database to their end users. So the key things here were that they needed schema flexibility. That was really crucial. And they tried to build this with a set of standard SQL DBs and two founders. And so for the resources they had, they couldn't solve that problem. And so that's where Cloud and this Couch model has really helped them get launched and make a big splash. So they now have a scalable solution. It deals with a large number of high level of concurrency during write, read, and view spikes. And their model was like a perfect fit for eventual consistency. Okay, so this was an excellent match. But I think the thing that really put it over the top was the ability to use MapReduce to do rankings and run their ranking algorithms and sorting algorithms in the database itself. So it allowed them to really take what were disparate parts of their prototype application stack and run them in the database as a single entity and really consolidate where their efforts were going in development. Okay. One of our other Cloud customers is a real-time analytics company. I didn't get the okay yet to broadcast their name, so I'll just tell you what they do and what we've been able to solve for them with Couch. They do high-rate advertising analytics, so clickstream analysis and social analysis in sharing. And they present that back to their customers so that they can see real-time, which was 24-hour summaries of how well new campaigns are working. Okay? And so one of their limiting factors was A, as business cranks up, they of course were starting to hit the limits of the scaling that they could do vertically, starting to worry about what happens if these contracts go through. But also their customers were really starting to ask for real-time results. And their ETL backend had a period of about 24 hours, okay, and it was running in Postgres in combination, or Postgres and custom analytics. And so what we were able to do for them using CouchDB was replace a lot of their complicated SQL stored procedures, tables, and in particular, they were trying to deal with entities and algorithms that just weren't well suited to SQL. For example, crawling a tightly connected social graph is a tricky thing to do. It's a very good fit for MapReduce in this case. So a lot of the complication and their internal development work was replaced with a single CouchDB document type that is structured, okay, because they are sending the data in themselves, and it has really only like 2 views, and it can present the results back. These views are not terribly complex, but they take advantage of this group level or different levels of granularity in the MapReduce correlation. And I'll show you that in a second. But really, this has been a huge success because they can bin their data, and their MapReduce results are computed on the fly, incrementally, and so they can present that back to their customers in a matter of seconds and not hours. And so for them, this really solved a real-time analytics problem, even though it's not a Hadoop back-end data warehousing solution. And so they're able to give their customers basically RRD-style summaries of the success of their campaigns. But really, another key thing, which was not just the time-based, but efficient way to map or to traverse over this ever-growing social graph, MapReduce was a huge help there. And so the biggest challenge there was helping them understand the paradigm shift between iteration, and in MapReduce, you're really thinking of clever ways to sort, okay? Yeah?
How big is the set that you're taking?
You mean number of records? What's that? I don't know this is total size of data. Number of records is 50 to 100 million documents, I think. So it's definitely not petabyte scale, right? But you're starting to talk about terabyte to tens of terabytes, depending on the document size. And I think that's one of the sweet spots of this type of a solution right now. But let me just go into a bit of a technical digression here about how we cut out, using Couch, a tremendous amount of code for them. One of the problems they had is they wanted to accrue summary statistics on a directed acyclic graph for a given node and all of its descendants, okay? And the information was stored in a way that they just know parent-daughter relationships. So in their case, they know the material path back up to the root node, so that just means that they know the path to the root, although that's something that can be calculated from the literature and MapReduce fairly straightforwardly. But what this allows you to do is instead of building procedures to build this graph in memory and then traverse it in the way they were doing in Postgres, this is a really simple MapReduce and really in the wheelhouse because each node, shown here in red, say knows the material path back to the root. And all you have to do is emit for each parent in that ancestor material path statistics about yourself as this node. And then they can be accrued by the view correlation engine. So this was a really excellent fit for their needs. And I think it's a great example of how these alternative databases are really well suited to certain problem sets. And the last one before we wrap up and head to lunch is case number 5, which I think is maybe most exciting, which is Ubuntu 9.10. So Ubuntu, and we heard a little bit about it this morning, the Ubuntu One project is deploying CouchDB with every version of 9.10. And so here's a quote from Elliot from about 2 weeks ago. One of the big things they were waiting on was the notion that the API was fairly fixed and that this was mature software. And this has really pushed the Couch community into tagging this as the official beta release. Okay, and now not jimmying with the API. And so when Ubuntu 9.10 is released, I guess this week, every single Ubuntu user, and it's about 13 million, I think, will have an address book stored in Couch. Beyond that, they have notes that they can sync to their local Couch and then replicate back up into the cloud when they're online. Beyond that, they see this as a key piece of their cloud strategy, and they'll be doing their best to teach application developers to use Couch in order to cloud enable their apps. And he goes on to talk about it. But for them, the real game changer here is this ability to replicate between on and offline data. All right, so I'll try not to keep us from lunch. Let me just wrap up a little bit. I hope I've given you an impression that CouchDB is a rapidly maturing project. At Cloudant, we especially see this as a key part of our vision for the cloud. I'll be glad to talk about that offline. But I think it has real disruptive potential. And you can argue about whether or not putting the application layer into the database server itself that can be then distributed is a real paradigm shift or not. But I think it allows you to do things that you couldn't do before. It allows you to do them easily. And I think we're starting to see that play out in the marketplace. This is really a project that's rapidly going from interest, from an alpha level interest project, to something that's being laid out by companies and at scale. So it's in production in quite a few companies now. And now that we've kind of settled on the API, the base functionality, and have gotten all the building blocks together to have a coherent application that is stable, we can turn around and start to focus on those requests of the people that chose not to use Couch for various reasons. And I think the initial focus was really on the API, on robustness, concurrency, and replication in the Couch project. And that's really changing now with an accelerating emphasis on features. I think ad hoc queries are something that's high on the list. And I think a way to minimize or lower the threshold to use the MapReduce engine for people that aren't comfortable writing MapReduce functions. And so along the lines of what you'll see in the Link project from Dryad Link, that's something that I think is likely going to be on the list very soon. Beyond that, we're certainly working hard on performance and bringing the clustering layer of Dynamo into Couch. And that's something that Brad's been working on with Cliff in great detail with a lot of code sharing, and we hope to push that back into the open source very soon. There are a few other things then before I step off, and I think that with these pieces and with clustering, you can start to see this come back into the big data sphere. And I'm not talking petabyte scale data to begin with, because it depends on whether you want your data fully indexed or you're really bound by streaming I/O concerns. For streaming I/O, there's no replacement for Hadoop. But as we start to talk about new storage engines for the Couch project, as we start to talk about new access patterns for how you build views, it opens up quite a few doors. And the other killer feature that if you actually write an application, you realize you need iterative levels of MapReduce to run the entire thing in your database. We have that in production now, and we're pushing that back into the open source as well. So I think there's a lot of very, what I want to say, disruptive development going on right now that's going to go back into Couch. And we hope that that is something that can bring us back into the sphere of kind of big data problems, or at least medium data problems. And we're very excited about the project. And with that, I'll wrap up. Thanks.
Questions?
It's a quiet bunch this morning. Yeah?
John, can you wait for a microphone?
I can repeat the question. Yeah, so the question was, this is kind of an analyst question, but what do you think IBM's role in this project is? So IBM hired Damien Katz after he took, I think, a year or two off of working completely self-funded and really got momentum behind Couch. He was then hired by IBM, where he works full-time on Couch. And my answer is, I don't know. I've been asked this in quite a few boardrooms. But I think that there's a solid backing behind the project now. That no matter which direction Damien goes, the project will continue to build and grow. And I think that the parts are in place here for something that allows you to go a whole bunch of different directions with this technology. Okay, you can just think about building big key value stores, right, that are spread across the globe, right? Or you can think about becoming an app house, for big enterprise level apps. Or you can think about being an app house for small, almost peer-to-peer ground computing style things. So I think there is a huge amount of opportunity. We'll be very curious to see what IBM's role is.